All right. Are we good? Okay. Thank you, Stephanie, for that wonderful introduction. Hello. Hello, everyone. I see we have, I think someone can't hear us, but that's all right. I think we'll get that figured out. I'm Jack, and today we're going to be talking about building your own balloon rocket, something you can do in your classroom or at home to have some fun outside of school. Let me share my screen. All right, so yeah, today we're going to be talking about a balloon rocket workshop. And teachers and students, if you have any questions or any input, if I ask questions, please feel free to use the Zoom chat and I'll try to keep an eye on it. And I think Stephanie will nudge me if I'm missing anything that you guys are saying. So before we get going, I'd like to introduce myself a little bit. So who am I? I studied at the University of Buffalo for my bachelor's degree in aerospace and mechanical engineering, and then got my PhD at Syracuse University. And currently, I am working as a research engineer at the Air Force Research Lab in Dayton, Ohio. And what I do there is I study the design of aircraft, fighter aircraft in particular. So the F-22, F-16, and the B-2 are all things that I look at on a daily basis. But we're not here to talk about aircraft and things that fly in the atmosphere. We're here to talk about something even cooler and further out there, all right? We're talking about space. And in particular, you guys are all going to be seeing these astronauts later today. And the real question is, how do we get humans to space? What do we do to get them up there? Feel free to throw some answers in the chat. I'll give you a second, but do you know how we get humans into space? It takes a lot of effort. All right, I see the chat buzzing, but for some reason I can't see it. Let's see if maybe I have to stop sharing really quick. Oh, I'm seeing some great answers. There we go. Yes, that is correct. It's rockets. There we go. Boom, some nice animation. There they are, all these rockets. But before we continue, I hope you all know how rockets work, but I'm going to let some experts explain it a little bit further. Hope you enjoy this nice video.
Of all the different methods of propulsion invented by mankind.
Oh, sorry. Can everyone hear that just before I continue? I just want to make sure. Let me. Okay, perfect.
Pure, unadulterated, heart-stopping excitement. Nothing really compares to rockets. Okay, I am about to initiate the launch sequence. Now stand right back and witness the explosive power of rocketry. I think we're going to need bigger rockets, don't you?
Well, boys, how about the biggest rocket of all time? Imagine 50 jumbo jets at full power strapped to a 36-story building. That's Saturn V. It takes something like this to catapult man to the moon. But where does the colossal thrust actually come from?
Inside a rocket motor, fuel is turned into gas through combustion, and the gas is then forced out the back. And the reason why escaping gas pushes a rocket forward is explained by Newton's third law of motion, which is, as I'm sure you'll remember from school, that every action has an equal and opposite reaction. That's the theory, but what we need is a practical demonstration. Now, as Johnny opens the valve on this pressurized gas canister, the air will rush out, but at the same time, an equal and opposite force will propel it this way. Come on, Johnny, open it up. There you have it, the basics of rocketry. Well, what did you expect? It's not rocket science.
The rocket's launch speed does not depend on the astronaut flooring the throttle, but on how quickly the gas escapes course, are hourglass-shaped because gas flows at an accelerated rate if it's forced through a narrow section into a wider end. The exhaust is crucial no matter what the size of the rocket.
All right. So some really neat stuff. Let's just go over those basics one more time. Right, as they mentioned, Newton's third law, every action has an equal and opposite reaction. So for rockets, that's, as they said, the gas flowing out the back of the rocket and pushing it forward. And what we'll see later today is that balloons use the same idea, where you blow air into it and that air comes out as exhaust and pushes the balloon forward. I think you've all seen when you blow up a balloon and let it go, it flies around. It's the same idea. But another thing that goes into rockets, not just the thrust, but there are a bunch of other forces involved that these gases and exhaust have to overcome. So in particular, the one that really counts is the thrust. So this pushes the rocket up into the atmosphere and into space. But while it's being pushed up, it also has weight pulling it down. Rockets are really heavy. So this exhaust and this rocket fuel needs to be very, very strong. Another force that you might be familiar with when you think about planes and when you're flying is the lift. This also helps pick the rockets up and raise it up into the air. But there's also a drag force. And this drag force is friction. Basically, as the rocket flies through the air, the air around it rubs against the surface of the rocket itself and pulls it back and tries to stop it from moving through it as quickly. Thankfully, engineers and scientists have developed rockets and engines such that the thrust outweighs all of these other forces, and we're able to get people to the moon and the International Space Station. So, students, I invite you to be honorary engineers today and build a rocket or build a balloon rocket using the engineering design process. And what our goal or our task is going to be is to hit a target on the wall, similar to how today we launch rockets into space to get people to a certain location. You have to be precise and you have to figure out how to get it to do exactly what you want. And the materials we have are a balloon, straw, some tape, and some string. And if you don't have these materials in your classroom, that's perfectly fine. They're easy to get. So you can do this at a later date if you guys would like. You can ask your teachers, obviously, or you can bring this idea home and have some fun there. It's very easy. All you need is a wall and these materials. And just so that you guys can see them a little bit better, I will show you all. See some straws, some silly, I'm using paper straws today. Some string. I actually have two types of balloons, one normal balloon and one, funny enough, is called a rocket balloon. It's a little bit longer, and run-of-the-mill duct tape. All right. And so using the engineering process, let's just talk about that a little bit further. So there are 6 key steps for the engineering process. And I think you might be familiar with the scientific method. The engineering process differs just slightly. But if you have that in your mind, you can kind of walk through the steps with me. We need to identify the problem. So really think, what are we trying to solve? What are we trying to do here? And then once we've identified our problem, we can move to brainstorming. And brainstorming is when we let our thoughts and imagination go wild and we get to figure out or think about all the possible solutions that there could be. Then we move to the design phase, where we take all of our ideas from brainstorming and whittle them down and figure out which ones have the best probability of success, which ones we think will work, and we run a little bit more of an analysis there. And then we get to build and prototype our designs and move into testing and evaluating. And this, as you see, moves back to the design process, because once we test and evaluate, we have to decide, is our design good, or do we need to improve it somehow? And once we've found a solution that we think works well, we then share that with the world. And this is how scientific advancement moves forward. And we get to move on from just getting people up to space, to the moon, and then to the International Space Station. All right, so let's think about this. Let's try to identify our problem. So take a minute to think about what our problem actually is and what we need to solve. And I'll give you guys about, 60 seconds to, if you're in a classroom or around someone, you can talk to your neighbor, or just sit there and think on your own. Maybe write something down and share it with the group in the chat if you can. Oh, well, I may have spoiled it for you, but sorry, if you've already, or if you thought about the problem that we're trying to solve, what we're trying to do, as I stated before, it's basically just restating what your mission is, right? It's how do we design a balloon rocket that will hit a target on the wall? Because we all know that if we just took a balloon and blew it up and then just let it go, I don't know if you guys can see me, so I'll stop sharing for a second. If you just let it go, it'll just fly. And that's not great. That's not what we're trying to do. We're trying to hit a target. And if you can see behind me, I've already set up an X on the wall. And so that's what we're going to aim for. So we can't just blow up a balloon and let it fly. So what could we do to solve this problem? All right. So next step, right, is brainstorming. And so to brainstorm, right, we need to think and be creative. This takes our creativity and also our curiosity into the design process. And as engineers, we need to be creative and innovative to think about new solutions that change the world. So any idea in this process is a good idea. Anything you can think of can work, but you need to exercise some self-control because we need ideas that relate to our problem. We can't find a solution for a problem we're not trying to solve. So now with these materials that I've shown and talked about, how do we think we can design a rocket or a balloon rocket so that we can hit this target right behind me? I'm already kind of giving away a little bit of it when you see the strings that are attached to the wall. But how do you think the balloon and rocket itself should be put together? And again, you can take about a minute. So discuss with some of your classmates and brainstorm some ideas and maybe throw some in the chat if you feel like sharing with the group. All right. Well, if I don't see anything going on in the chat, so I'll just move on. Basically, what we want to do now is design these rockets to do our described task. And so that's our design part, right? So whatever you thought about, so it could have been attaching the straw to the balloon by wrapping the string around it, attaching the string to the wall and then taping the balloon to the string and letting it go, sticking the straw into the balloon and letting that fly as well. And that's all part of the design and brainstorming process. But for this aspect, now we have to think about two things, grit and optimism. So grit in the design process is being determined and trying until you succeed. Failure is always an option because that's how we learn. So we try something, it doesn't quite work the way we thought, and we improve it. And that's where the optimism comes in, where we have to believe that we will find the right solution or a good solution for our problem. So let's put together some of these balloon rockets. And so the way that I've been doing it is I'll show you an example of one that I have, is taking the balloon itself and then taping the straw, after cutting it, taping the straw to the top of the balloon. And so this is my idea, my design. This is one balloon. We have 4 that we'll talk about in 2 seconds. for a few seconds. But whatever you were thinking of, you can always try it. That's the beauty of this process. You can try whatever you like and see how it works and see whether or not you like it better than another option. So that brings us to our next stage, which is build, test, and evaluate. And so when we build and test and evaluate, we have to think about it and then redesign. And so I've designed several different rockets for us to look at. So we have 4 rockets, and I will show you each one of them individually. And this process takes some self-control, right? We don't want to rush. We want to test our design and we want to make improvements. And we need to, by evaluate, we need to document what we see. And so now for the fun part, we can, oh, I'm seeing some good answers here. So here, let's look at what I have as an example, and you guys can do this later as well. So the first balloon we have is a smaller balloon with an orange small balloon, again with the straw attached. So we'll just put that up here. Now we have a bigger balloon, same size or same type, round balloon, similar straw attached here. Okay. And then we have a rocket balloon, but if you'll notice, the straw is attached perpendicular to where the nozzle is. So that's an interesting idea. Let's see how that works. Design number 4 or 3, and then design number 4 is a red balloon, rocket balloon with the straw attached with the nozzle. So, as a class or as students, I'd like you to think, which one do you think is going to work the best and why? So this will be like creating our hypothesis, right? Which balloon do we think will work best? And then we'll test them and go from there. So we'll test the first balloon, or the orange balloon first. It's very easy. I have these nice clips. So you pull that tight and then let it go. Woo! Wow, that was really fast. And that seemed to work really well. All right, so that's the first balloon test. Let's do our next balloon, which will be the yellow balloon. Again. Oh, I seem to have made a mistake, and I attached the string and the straw in a reverse way. But we can see how this will work, right? So if I let go, what happened? It went the wrong way. And that happens, and that's okay. When you're testing and designing things, mistakes are fine because sometimes they result in interesting solutions. So now here is the green one. Again, with the perpendicular or not aligned straw. We'll see what happens here. Not only does it make a fun noise, but it also just rotated around the string. And finally, our red balloon. Here we go. You can all see this great. All right, again, that one worked, but it was interesting because it didn't work as well or as quickly as the others, or as the first one. So I'll leave it to you guys to figure out or decide which one you thought was best. But what we can notice here is that that red one moving and kind of inching along is similar to what drag does on a normal rocket. The friction between the string and the straw actually pulled it back slightly and stopped it from moving as quickly. Okay, so we've tested, we've evaluated. We're not going to redesign, we don't have time for that, but with the information that we just saw, we can kind of guess as to which one was the best in this instance. And so once we've found this solution, we share it with the world. So now you can go to all of your friends and family and say, hey, I know that this balloon works the best in the balloon rocket workshop where we try to hit a target. And the reason for sharing your solution is you want people to know about what works and what doesn't. And this is how we advance technology, we advance science. It's how everything improves and gets better. And we honestly, from 100 years ago to today, that's how all this technology came to be. I'm talking to you through a computer, through a camera and a screen and the internet, and that wasn't possible decades ago, years and years ago. So this, in particular, sharing your solution requires two important characteristics. One is social intelligence, and social intelligence in particular is the way you communicate your ideas with one another and how you interact. You don't want to argue, you don't want to yell, you don't want to fight when you have an idea and you're talking. You want to discuss it calmly and collected. You want to hear what the other person is saying so that the two of you can come to either an agreement, a compromise, or just understand where each other is coming from. The second thing is gratitude. If you worked on a team, you should be thankful for all of your teammates and what they contributed to your project. Well, with that, I'd like to say thank you for joining me. And if you have any other questions or any comments you'd like to share, please feel free. I don't know how much time we have left. I may have gone over, so I apologize, but this is great. I hope you all enjoyed.
Thank you, Jack. And yeah, if anyone has any questions for the next couple of minutes, please share in the chat and we can cover those real quick.
Yeah. I don't know if you guys can see, but my flight suit is actually from Space Camp. I went as an adult, so it is for
Awesome.
adults as well as kids.
All right.
But yeah, if there's nothing else, I hope you guys enjoyed it and have fun using the engineering design process to figure out things on your own and hopefully do some cool balloon things. Yes, Emmett, I do enjoy my job. Unfortunately, no, I'm not an astronaut. Not yet, at least.